So in this video, we're going to look at the edit distance problem. So the idea here is you have two words, and you want to see the minimum number of insertions, deletions, and substitutions you need to use to transform one word into the other. So for the example of food and money, the first thing we're going to do is we turn F into M. So that's a substitution, sub F for M. The next thing we do is another substitution, O for N. Now we're going to insert an E, so this one's an insert. And lastly, we do another substitution, D to Y. And that's one way we can transform food into money. Now, the goal is to figure out the minimum number of these operations we can use to do this process. In particular, for any choice of deletions and insertions, we can actually draw an alignment of the two words. So here, the alignment represents F had to be turned into M, E had to be inserted because there was no E before, and D had to be modified, and O had to be modified to N. So the alignment basically shows you where insertions and deletions have to happen based on the spaces. The spaces imply insertions and deletions, whereas anything else indicates we must have done a substitution to transform the top word into the bottom one. So if we knew the alignment in advance, we can just count the number of times we didn't have a match. Every time we don't have a match, we either had to do a substitution, insertion, or deletion. So the number of columns in this alignment roughly gives us the edit distance. But that's not the approach we're going to use. We're going to solve it directly with dynamic programming. So first we need to think about the problem recursively. And again, we're looking at optimal substructure here. So the idea is if we already decided in advance some of the insertions and deletions, so here we've already decided some operations in advance, and now we're in the middle of the process. Then the optimal thing for us to do in the future doesn't depend on these past decisions. So if we remove the last column, which is this column, or all the previous ones, then of the remaining columns, the shortest edit distance will be the shortest for that subsequence. So it suffices to solve optimally the subproblems to solve optimally the whole problem. So optimal subproblems solutions give us solutions to the overall problem, just as we've seen before. And always keep in mind the shortest path in a graph example. It never helps to have a long path in the middle because shortening that path shortens the overall path. If you can reduce your traffic in one place, that helps your overall time. Okay, so we can also prove this directly by contradiction. So if you could have a shorter edit sequence for the subproblem, well then just glue that edit sequence to the rest of the edit sequences, and we get a shorter edit sequence overall. And again, it's just because the cost, or the number of edits, is computed by adding. And if we computed the min of a sum of things, well then we could separately min each individual. So that's the optimal substructure property here. It doesn't benefit us to do something suboptimal over here because it's not really affected by everything we've decided in the past anyway. Okay, so now let's try to solve the problem. So if we just look at the middle of the problem, we're at sum column I. Well, we can either insert, delete, or substitute the value of the top string in order to get the character of the bottom string to match. And to do this, we're going to define a recursive function, edit ij. What edit ij is just computing the optimal edit distance for the substrings a1 through I and b1 through j. So it's looking at the beginning of the array first and saying what's the optimal thing we can do for just this block. In particular, notice I does not need to equal j. So you could actually have your subproblem being the top string is alg and the bottom one is money. So in this case, we already have a mismatch in terms of the lengths. And so we'd have to have some kind of insertions or deletions. So this is basically what our subproblems look like. We'll look at the rightmost column and decide what we should do. And at the very end, we are going to return edit distance of mn so we can get it for the entire strings, not just the first few letters. So that's the problem we're going to solve. And now how do we define the recurrence? Well, again, we have three options. We can either insert, delete, or substitute. So in the insert case, that means that the optimal thing must have had a space in the top row. So if the optimal solution has a space in the top row, then in order to get from a space to a U, we must have done an insert. An insert costs one operation, and then we recursively will edit I through j minus 1. Now it's I through j minus 1 and not I minus 1 because we did an insertion. So we didn't actually modify the top string at all. We just modified the bottom string, or processed the bottom string. We still have to solve the rest of the first word. So this is a way to add a space in the top row. On the other hand, if we look at deletion, it's the same idea. Now we're processing the top string, but not the bottom string. So if we did a deletion, we killed R, and now there's nothing here. So we've processed more of the top string, but the bottom string has remained unaltered. But we still get a +1 because we did some operation. So the key thing here is which array is moving is the key difference between insertion and deletion. It's changing the subproblems we care about. And then lastly, we have substitution. This one's a little more interesting because sometimes substitutions are free. So if the value of the string is the same in the ith column, then we don't have to do anything. There's no +1. They're already matching and we can move on. Otherwise, if we do a substitution, we changed R into U, and so we processed one last character from both strings, and so we have to now move back for both of them. So then the induction fairy will solve the rest for us, and we've decided to do a substitution. So those are our three options, and so if we just pack those into a recurrence, it'll look like this. So in particular, we can either insert, delete, or substitute. There's three options. And in each case, we get the corresponding subproblem and cost. And notice here, if the substitution has both characters matching, like up there, then this will be cost 0. So either we insert, delete, or substitute, we try all three. The recursion fairy, by the induction hypothesis, computes the optimal solution for the subproblems, and so the opt for the subproblems plus the operation we did gives us the total number of moves, And then the min over all these number of moves gives us the minimum total for the entire process. So the last thing are the base cases. Well, the base cases happen when one of the strings becomes empty. So say the top string is empty, then we have to do insertions for all the remainder of the bottom string. So that's j insertions when I is off the board. So when I equals 0, so we've completely processed the first string, then we have to do j insertions to get the bottom string. And similarly, if we run out of the bottom string, then all we can do is delete things, and so we're going to delete I items, because that's how many are in the top string. And so that gives our overall recurrence. So there's 3 possibilities of operations. We recursively compute the rest of the solution given each operation, and then we optimize over all those final solutions to get the best one. So that's why the algorithm is correct. So now for the dynamic programming stuff, the subproblems are pretty clear. I can be from 1 to m, j can be from 0 to n. That's just because the base cases are at 0, and then the lengths of each string are m and n respectively. What structure can we use? Well, we're just going to have an array that can hold each subproblem. So edit of ij stores the solution of the function edit ij. Now for the dependencies, it's not too bad because we only depend on one item in each case. And if we draw these out, well, we have our ij entry. It depends on ij minus 1, which is the same row but previous column. And that's when we do an insertion. If we do a deletion, then we get this one. And lastly, we have I minus 1, j minus 1 for the substitution. So we depend on all 3 of those. And so a valid ordering would be to have I in an outer loop that goes from 0 and up to n, or m. And then j go in an inner loop from 0 to n. So overall, it would look like this. And then your recurrence inside. Now, if we look at the space and time of this algorithm, well, the size of our array is O of mn. So that immediately we have the space. And then edit ij, remember we're just doing a min over 3 things and some sums and if statements. So it's constant per subproblem. So overall it's O of mn time. Constant subproblem per subproblem, and then O of mn subproblems. So O of mn times O of 1. And overall, here's the pseudocode. You can look at it in the text, and it implements exactly what we described above, just with, the base cases are enumerated outside the main loop, but otherwise it's the same. Now, one interesting thing is this just computed the length, right? This computed the number of operations we had to do. But if we wanted to actually compute the operations, we can always get the solutions from the table. So if this was the entire edit table, and each entry is just edit ij. This is edit ij. For example, this would be edit 1, 1. Then, or actually that one's edit 0, 0. So the way we compute the solution is we start at the very end. So maybe the end of the solution, because we plug in mn at the end, we know this is the end of the solution. And then at each point, we made a decision. So to get from mn, which is the end, we made some decision. And that decision, we can figure out where it came from. So if this value was 6, and we know the previous values, then we can figure out where it came from. So for example, here we have an I and an I. We have this is 6, and we know edit of I minus 1, j minus 1 is also 6. And so we know we must have done a substitution with no character changing, just by looking at the recurrence, right? So if we just look at this, we know this value, and we know each of these values, and so we can just brute force figure out which option, which choice gave us this optimal value. So by looking at the table, we just see that, okay, if we trace back in time, this gave us the optimal value, and so we know it was a substitution. And then we can go back one more step. Well, what did we do before that? Well, we did another substitution. We just have all of these substitutions, which are these ones highlighted. So we can trace back in time, figure out which thing caused our choice, and continually follow these arrows. So you'll see this trail of arrows here. And if we just follow this trail of arrows, we can read off what choices we made at each point, and so print those out, or return those however we want. So by following the arrows, we can actually compute the final solution, not just the distance, in linear time, just by searching through the table in that order, where we know which thing caused our current value, and so we can print out that operation we did, and then we can just keep tracing back. We know which subproblem generated it, so we go up the table correspondingly. So for example here, this arrow indicates that we, I believe, inserted something, and so we would go to the I minus 1j case of the m to continue up. And then we keep tracing up and following until we eventually hit the base case 0, 0. And that gives the full solution. But in general, you don't need to, for like homeworks and things, you don't need to tell us the solutions. But if you ever needed to, you can compute them quickly once you know the answer, like once you've filled the table with the values.